Hi. Today we're going to talk about precision and accuracy and how they relate to measurement errors. Actually, when I started creating this lecture, I thought mostly in context of measurement error or experimental error. In other words, you do an experiment, you come up with a result, and you decide how precise or accurate are those values. But then I realized that in engineering, it relates to other aspects of engineering, including forecasting and certainly manufacturing or other achieving specific engineering objectives that you might want to be achieving. So in that case, I wanted to talk about different aspects, and I have principally, I'm going to describe this by way of example. You should have already watched the precision accuracy animation, which showed you a description of, it's kind of an analogy based on, there were actually two pieces to it. One piece was a target, achieving a target, basically shooting an arrow at an apple. And the second piece of it was related to the achievement of landing on Mars and how precise or accurate NASA was able to achieve based on how much information they had. So make sure you watch that. I think it's pretty much self-explanatory. We're going to go into a little more detail in this presentation. All right. So as I said before, precision and accuracy come both into play or in context of measurements. So you might make measurements of length, thickness, velocity, or acceleration. So how good or how precise are your measuring devices? Certainly with for example, when you do like physics experiments, you sometimes the measurements are indirect rather than direct. You may measure gravitational constants, other things. So measurements are really speaking to like either direct measurements or experiments. Forecasts may be in the context of the depth of extreme storm events. You might just, and we'll talk about that a little bit more. Hurricane tracks, future concentrations. In the case of, for example, a spill of some contaminant, you want to do a forecast in the future. You really got to think about how precise or how accurate are those forecasts going to be. And lastly, and this is one that came to me kind of later, it really talks about how precise, how accurate are you in achieving specific engineering objectives. You might be manufacturing to specific particular specifications, such as let's say you're creating sheet metal and you got to manufacture it to some particular thickness plus or minus some value. Or as in the case of like automobile manufacturing, you need to have sort of a fit. You want to make the say the distance between the door and the door frame be less than some value that you want to achieve. And as I mentioned with that animation, we were talking about the Mars landing, so that also relates to precision accuracy. So as the when we talk about how good of a value is or a measurement, either a measurement or how good is it, are you at reaching some objective? There's two ways of really thinking about it. One, are you precise? In other words, if you make a measurement, are your other and they make repeated measurements, are they likely to be clustered about closely about some value? So are the values reproducible or repeatable? And secondly, are they accurate? Are you actually getting to the correct value? So if we think of it in terms of manufacturing of sheet metal, accurate, and you want it to be, say, 2/100ths of an inch thick, so it's going to be really thin. If on average you're achieving 2/100ths of an inch, then you would say that it's accurate. But if it's not precise, in other words, if some of them are larger or smaller outside of certain specifications, you might say that that value is not precise. Okay, and frequently you'll see this, and if you look on the web, you'll see this kind of target analogy. So in this case up here, if you're achieving the center of your target repeatably in a clustered about some small region, that would be called high precision, high accuracy. And then over here, and you can see higher accuracies in this direction. So here's high accuracy where the average is essentially near the center of the target, but you have scatter about that value. It's not tightly clustered. And then you have another situation where you have high precision, low accuracy. So you can see you have clustering. In other words, your values are repeatable or reproducible, but they're not hitting the target. They're not hitting the value that you want them to be. And then finally, you can have low precision, low accuracy, which is obviously not desirable in most cases. Low accuracy in that the average is not the center or your objective location. You're in the center. And low precision in that they're not clustered about a certain value. They're unable to reproduce the values from one shot at the target to the next. So that's a good way to think of precision and accuracy and how you can have one but not the other. All right, so here is, I'm going to go through a couple of interesting examples. This one actually came up in a consulting project that I'm currently involved in. Frequently, we use something called the 24-hour 100-year storm depth. 24-hour, it just relates to the duration of the storm that you're thinking of. So it's basically rain. How much rain are you going to get over a 24-hour period? And when we refer to 100-year, that means that that the value, what storm depth are you going to achieve? That's or what storm depth would you expect to see that's only exceeded once in 100 years? So that's obviously going to be like a large storm, because if it's only exceeded once in 100 years, that's going to be something that you're not seeing from one year to the next. So for example, the 50-year storm depth would actually be smaller than the 100-year storm depth, and the 10-year would be even smaller than that. And then obviously the 200-year storm depth, so it's a storm that you don't expect to see once in 200 years, that's going to be even larger than the 100-year storm depth. So the U.S. government, through the National Oceanic and Atmospheric Administration, NOAA, produces something called the Precipitation Frequency Atlas, the U.S. The last one was updated in 2015. Before that, we had one that goes back a number of years. All right, so these values are used in hydrologic design. If you're designing a dam, if you're designing a stormwater system, if you're designing a canal that's going to be handling either like river or stormwater, if you're designing, say, bridge embankment. I mean, all kinds of hydrologic design or hydraulic design, you need to know this 24-hour, 100-year storm depth. It's kind of a convention. People say, well, let's go for the 100-year storm, but if it can handle that, then we're happy. So this gives you a sense of the kind of raw data that's used to create this 24-hour, 100-year storm depth. And this is the max on the horizontal axis. It basically goes from 1946 to 2014. And on the vertical axis, it has the maximum storm depth in inches. So each year, they say, what was the maximum storm depth? And they would plot that point. And the orange is for Provincetown, and the blue is for Hyannis. And the reason that these are both obviously Cape Cod locations is because the project that I'm working on right now is in that area. So this is the raw data. The actual 24-hour, 100-year storm depth values can be found in this NOAA Atlas 14, and they actually have a web page, and you can point to location, and they'll tell you, oh, the 24-hour 100-year storm depth is X, and in the area of my interest and near Wellfleet, it's about 6.9 inches, so it's a big storm. We don't get those too often. All right, this is kind of a compilation of the 24-hour 100-year storm depth. You can't really make out this legend, I know, but the brown are essentially the lowest, and as you get towards the coast, they get higher. I think these brown values are about 4.5 inches. These green ones are about 7 inches or 6.5. And there are some sort of peaks in here caused by, usually it's caused by orographic effects, where you have mountains, essentially mountains or high topography, and as the weather patterns or the air blows over these things, it has to elevate. And you frequently have on the upstream side, you'll have like high rain values. All right, so this is kind of what you get from that. And this is sort of the standard procedure. You get a 24-hour 100-year storm depth, and you tell the client, here's what we're going to design around, okay? However, and my client said, well, yeah, there's this one value, but is it really how precise is that value? Could the value actually be much higher? And I said, well, I don't know. And actually the value that I'm referring to is the water elevation on their property. And it's the result of activities that are occurring, or actually a dam that's being constructed on a neighbor's site. Okay, so I went to that Atlas 14, and what I found, and this was kind of interesting because I didn't actually realize that this information was available. But the NOAA, when they created the Atlas 14, they also plot these confidence intervals. So it's kind of like that plus or minus that you'd say, well, if you were measuring something, you say, well, I know it's going to be the height of some, or the length of some rod is X value, but because of the lack of precision in my measurement, it might be plus or minus. So that's kind of what this is. So there's this confidence interval. So what we're going to look at is the 100-year storm depth. So here's 100-year. Here's the precipitation. So that 6.9 inches essentially here, as you can see if you cut across. But they're saying this green value is the upper bound of the 90% confidence interval. The red is the lower bound of the 90% confidence interval. So according to NOAA's statistical analyses, they're saying the actual 100-year storm event could be anywhere from as high as here, because that's a 100-year event, about somewhat over 9 inches, and as low as here, which is about 5 inches. So it's almost a 4-inch band. So I have to go back to my client and say, well, this is the storm depth that they're designing it around, the 6.9, but the actual value could actually be much higher, and within a not unreasonable possibility, it might be much higher than is being planned for. So that's kind of an interesting problem. And this is something that's not frequently taken into account doing hydraulic designs. Now this is kind of a made-up thing that I made up, and I really wanted just to show you what a frequency histogram is and how it relates to the concept of precision. But I said, what if you were measuring the distance between 2 points and you had two different methods? I don't even know what the methods are. This is, as I mentioned, this is kind of made up. And let's look at the kind of spread or that occurs, or how precise one of the methods is relative to the other. Now you can imagine these are what are called frequency histograms. So on the horizontal axis is our length. It's essentially the measured distance in miles. And the upper axis is the frequency. So essentially, if I look at this value here, and it's a little hard to make out, but these bars are over intervals of 0.2 miles. So it's really like from 1.06 to 1.08, we had essentially, you see, about 19 measurements, all right? And all of my measurements were essentially between 98 and 100.8, I believe that says. I don't have my glasses on, I'm sorry. 102.8. So there is a particular range, this is sort of a characteristic range. If So that's method one. And and I'll just mention that if we had a perfectly precise measurement, if it was 100% reproducible, we would just get one bar basically in the center, where our wherever our mean measurement was, and it would basically, if we had 200 measurements, the frequency would basically be 200 because all the measurements would be exactly the same. So the more we deviate from that, the more spread out they are horizontally, the less precise the measurements are. So obviously this one, these are in the same axis. These one we have measurements that occurred all the way from 95.6 to 104. Obviously there's more scatter here, so we say that this is less precise. So it actually says it here, method one has a higher precision, so it's a more precise method of estimating. So keep in mind these are called histograms. Histogram, kind of a chart. And then I threw in a third chart down here, and I said this one, and you can see this one is also in general is more precise. This would be number one here that we saw in the previous. Here's number two. Here's number three. So this one is also narrow band and horizontally. So we'd say that it's precise. But in this case, you can see that the center is offset relative to the center of number one and number two. Obviously, those are kind of like the best estimate of that distance. So you might question that the third one, this third method that we're using, it may be precise, but possibly it's not accurate in coming up with the distance. All right, this actually came out of, this is another example. This came out of the New York Times just the other day. I was looking at it, reading this, and I thought, that's interesting because it really relates to what we're talking about. In this case, they're forecasting, and this is Hurricane Irma, I believe it's from 2018. And what they're doing is they're forecasting. They know the hurricane is at this point right now, at the center. Let's do this in green so we can see it. So here the hurricane is down here, and they're running computer simulations, and in doing these computer simulations, they're trying to evaluate, in each case, they're evaluating with slightly different parameters. And what they find is they get different tracks depending what parameters. You can see in one case it's like that. Many of them seem to fall along this area here, but there are some that are like way out here. So you would certainly say that in forecasting the hurricane track of Hurricane Irma, that they lack precision in the ability to really know exactly where it's going to be. But what they commonly do, they'll create these circles. In communicating to the public, even though it's imprecise, they got to give some kind of estimate of the track so people can prepare. So in this case, they draw these circles. The centers are essentially the center of all the different hurricane track simulations. And then they draw these circles that imply the confidence they have as to where the actual plume is, hurricane center is going to be. And then beyond that, when they actually present it to the public, they present it like this. And frequently, and the point they make in this article is that the public doesn't really understand exactly what these cones are. These are really intended to suggest the confidence as to where the center of the hurricane is going to be, not where impacts are going to be. So impacts might go well beyond what's shown on this map. All right, this is one last example that I wanted to show you. You can imagine that you have two rulers, and we're only showing kind of the end of the rulers from 98, 99, 100. These are in centimeters. So we have one ruler where we have millimeters being drawn, so that's why it has these many small gradations in here. And then the other ruler, it only has centimeters indicated. Okay, so you really, when you're measuring with this ruler, you can really only say something like it's 99. We know, for example, this one is 99. And then I can estimate, basically eyeball it in and say, that looks like it's about 2/10 of beyond 99. So the precision to which you can actually, or accuracy to which you can actually make and report a measurement is frequently a function of the technology that you're using, or the device you're using to do the measurement. Okay, and I'll just show you, I went beyond that and I said, well, what is the length of this rod? Imagine this rod actually extends far off to the left. We're only seeing sort of the rightmost end of it where we're doing the measurement. So in the first case, we see it's basically 99.1, and it's almost at 99.2. So we can report it as 99.19 with a confidence interval of about 0.01. So what we're saying is that that 99.1 is known completely or absolutely, and the 9, that last digit, there is some uncertainty. So you always report, whenever you're doing a measurement, it's always the case where you're going to have all the digits are going to be known precisely or exactly, and there's usually one last digit on the right which may have some error band or uncertainty associated with it. Same thing with this one. In this case, we reported as 99.2. So that 0.2 is probably some, it could be 0.1, it might be 0.3, maybe it's something around that. And it's usually, like in this case, it would be like plus or minus 0.1. I mean, I'm basically kind of approximating that. In fact, in looking at it, I might say, maybe it's 99.2. I might go beyond this and say, probably not. Probably I would just stick with 90. If I really had that ruler and I was trying to measure this rod, probably that would be about the best I could get. Although I might say the confidence interval is slightly less than 0.1. Maybe it's only 0.08 or something like that. Okay, so this really gets to what precision and accuracy of measurements is. And the next thing we're going to deal with is significant figures, which really relates to how you report value, report forecasts, report measurements, we'll talk about that in the next presentation.